Hello everybody, and welcome to the latest edition of the Physics Corner, the video series in which we solve introductory physics problems. I'm your host, Dr. Christopher Cirola. Today's episode, we are going to solve one last time an Atwood's machine problem. In this case, we're solving for the speed of the masses as they drape across the Atwood's machine, incorporating the effects of the pulley wheel. So, in previous episodes, we have solved for acceleration and for speed. We've solved for acceleration both with and without the pulley wheel. We've solved for speed without the pulley wheel. Today is with the pulley wheel. And because the pulley wheel is a rotating object, we have to incorporate rotational motion to solve that problem. So, let's go ahead and get started. So, this is an energy problem. Now, like many energy problems, they are very good at solving for speeds. And that's what our question is. Let's take a look at our situation. We have a small mass here, a large mass here, and a pulley wheel here. The small mass is a height h below the heavier mass. When the system is released, the small mass gets pulled up, the pulley wheel rotates, and the larger mass drops. We're going to assume that this distance is 1 meter. We also have various masses and the size of the disk, and of course we round off little g to 10 for demonstration purposes. The only thing we're interested in this particular problem is the speed. So, how do we solve for speed? Well, this is an energy conservation problem, so let's do energy conservation. Depending on how your instructor or textbook likes to write it, we could talk about the energy going into a problem equaling the total energy coming out of a problem, or if you prefer, the initial or original energy and the final energy. I'm not too worried about the specific ways to say that, except that the concepts are there, right? So, what kind of energy do we have going in? Well, at the beginning, nothing is moving. It says specifically, when released from rest, therefore, nothing's moving, therefore, no kinetic energy of any kind. The height is chosen to be 0, where mass number 1 starts, and mass number 2 is a height h above that. So, the only possible source of energy to start the problem is the gravitational potential energy of the second mass. Gravitational potential energy, let's write it over here to the side, in general terms, is mgh. So, let's put in m2 gh to get started. And that's it. There are no other sources of energy for this problem at the beginning. Again, because nothing else has a height to it, nothing else has any motion. Now, in case you're wondering, what about the pulley wheel? Is the pulley wheel not a height above that? Yes, but the pulley wheel never moves, right? The pulley wheel doesn't move vertically, I should more specifically say. The pulley wheel rotates, but it doesn't move up or down, and therefore there's no gravitational potential to worry about for the pulley wheel's case. So, none there either. All right, at the end of this problem, mass 2 has gone down to height 0, so there's no more gravity potential there, but mass 1 has been yanked upwards, so it has accumulated gravity potential, and we can illustrate it that way. Also, both masses have moved and are moving at some speed v, we'll call it, at the end of the problem. And so even though mass 2 is going down and mass 1 is going up, kinetic energy, as you recall, equals 1/2 mv squared. And since we're squaring a velocity, the direction doesn't matter anymore. So mass 1 has a kinetic energy of 1/2 m1 v squared, and mass 2 has a kinetic energy of 1/2 m2 v squared, like this. Now, how do we incorporate the pulley wheel? Well, the pulley wheel rotates, and so because it rotates, because it's a physical object with mass, that implies it also possesses a kinetic energy. What kind of kinetic energy? Rotational kinetic energy. So we're going to make a small addition here. We're going to put a subscript L on this first kinetic energy. Now we need to, because that is what we call linear or straight line kinetic energy. But the question we're asking about the pulley wheel is rotational kinetic energy. That is equal to 1/2 multiplied by moment of inertia multiplied by angular or rotational velocity squared, and looks like this. So, if we want to incorporate what's happening with the pulley wheel, we need to include its rotational kinetic energy, and we simply add it here. Again, remember, energies are all scalars, which means if you want a total, you just simply add everything up, right? So, that's exactly what we've done. Now, here's the next step. What do we do with this? Now, if you look at first glance, we have introduced, because of this term especially, a whole host of unknowns. We don't know V. We also don't know I or omega right now, so how do we incorporate that? How do we deal with that? I is moment of inertia, and the clue for dealing with that is this statement here. We're going to assume the pulley wheel is a solid disk. If we assume the pulley wheel is a solid disk, then the formula for moment of inertia of a solid disk is 1/2 mr squared. Now, I'm going to put a subscript little letter p on that mass to make sure that we know that that's the mass of the pulley wheel and not either of the other masses. Right? So we do have to distinguish that. R is the radius of the disk, and this is a rotation around the center of the disk, and that is exactly what's happening, right? It's rotating around its center. So, moment of inertia of a solid disk. Now, in actuality, the disk is probably not a perfect cylinder and so on and so forth, but this is a good first step. This is a first good modeling attempt at what the disk is capable of. Okay. What about the velocity part? Well, in terms of velocity, the linear velocity at the edge of a disk is equal to the radius of the disk multiplied by its angular velocity, which we symbolize with the little letter omega, the Greek version of the little letter W, right? Like that. And that means that this pulley wheel is rotating. That's what we're talking about. And the velocity is a point at the edge of the disk. Now, why do we have to worry about that? Well, the velocity or speed at the edge of the disk is the same as the velocity of the string. Again, I keep saying velocity, I mean speed. And the speed of mass 1 and the speed of mass 2. They're all connected together. So that is what we want. We want that. Now, the formula says omega squared, so we need to turn this into omega squared. So first, solve for omega. Omega is equal to V divided by capital R. And omega squared then is V squared over R squared, like that. Let's go ahead and check out this rotational kinetic energy term by itself first. So kinetic energy of rotation is 1/2 I omega squared. But now it's 1/2 multiplied by the moment of inertia, which is 1/2 mp/r squared, like that. And omega squared is V squared over R squared. Now, why are we doing this? We'll show you in a moment. A couple things. First off, notice that this 1/2 and this 1/2 are separate 1/2s. So we can't eliminate one of those. Make sure that you've got both of those there. This 1/2 is fundamental to the equation or the formula itself. This 1/2 comes from the individual shape. In this case, we're using a solid disk. If, by the way, it was a different shape, if it was, say, a solid sphere or some other kind of shape, we'd have a different fraction here. But this is a solid disk, and that happens to be the case. So don't forget, we do have two of these 1/2s to worry about. Also, one of the reasons for writing it this way is that we get rid of one of the bits. So R squared here divided by R squared there, right? That cancels. So put everything together. 1/2 times 1/2 is 1/4. We have MP and a V squared. And notice what we've done. We have taken what looked like a rotational kinetic energy term and turned it into something that looks very much like a linear kinetic energy term, right? A fraction, a mass, and a speed squared, linear speed squared specifically. And that allows us to add everything together now where we couldn't do it before. So let's take this equation and rewrite it. So M2GH equals M1GH plus a 1/2 M1V squared plus a 1/2 M2V squared. And now substitute 1/4 MPV squared like that. That makes a big difference because now we can see lots of terms have the V in them. Everything else is known, right? All the masses are known. H is known, that's the 1 meter. G is known, that's our good friend, 10 meters per second squared. So everybody's known. So at this stage, it's a matter of consolidating. So to consolidate, notice that the equal sign is over here, right? So let's subtract this term here to the other side and put all the V's together. So a 1/2 M1V squared plus a 1/2 M2V squared plus a 1/4 MPV squared on the left, M2GH minus an M1GH on the right. At this stage, it kind of depends on how you like to consolidate things, but if you notice, everybody over here has a 1/2 V squared term in it. So let me separate that out. So I have a 1/2 Now I'm going to write this way. You'll see why in a moment. M1 plus M2 plus 1/2 MP. Notice that 1/4, 1/2, that's how I get that. And a V squared over here equals, then consolidate on this side, M2 minus M1 GH on the right. Okay, so almost done, but let's take another page to finish this up. Okay, so to have this out here in front of everybody one more time, we rewrite our equation so everybody can see what we're doing. Like this. All right, everybody. Now, let's divide or move all of these things here to the right-hand side. So I need to multiply by 2, or divide by 1/2 if you prefer, to get the 1/2 over. So that will be a 2 M2 minus M1 GH there. I need to divide by this inside the parentheses. So that will be M1 plus M2 plus 1/2 MP, like that. And that's V squared, mind you, right? I don't want V squared. Ultimately, I want V. I want speed. So take the square root. Now, you could write this with a gigantic radical symbol, or you could simply just put this in parentheses and to the 1/2 power. Same thing ultimately. And let me go ahead and separate a few things out. I've got, again, a reason for this, which I'll show in a moment. And notice everybody here has to be under the square root sign. Do it like that. Okay, so here is our algebraic solution. Okay, what does this mean? Well, a couple things. First off, let's compare this to the solution you had when we did not use the pulley wheel. When we didn't have the pulley wheel, this term here was missing. Cover that up. And that turns out to be exactly the same solution you had in the past. Okay. And also notice that if the masses are the same, M2 minus M1 will be 0, and there'll be no speed over. In other words, the mass is hanging still, and so on and so forth. Right? If you want to see more about the ins and outs of what the meaning of the solution is, I advise you to go check out the earlier video, the part 2 of the Atwood's machine, where we solve for speed without the pulley wheel. But now that we've got here, let's go ahead and plug in some numbers to see what happens. So 220 grams minus 200 grams in the numerator, 200 plus 220 plus 1/2 of 500 in the denominator, like that. Then we have a 2, G is 10 meters per second squared, H is 1 meter, and don't forget everybody square rooted. So the way to work this in your calculator is to do this calculation first, multiply by everybody here. Once you get everything inside the parentheses done, then take the square root. When you do this, your speed will be a value of 0.77 meters per second, and that will be your answer. Okay. One last bit. What would happen if we did not include the pulley wheel? What's the effect of the pulley wheel? So, without the pulley wheel, our speed was 0.98 meters per second. What does this mean? Well, it means hopefully what you think it might mean. It means that if we're making the pulley wheel rotate, that requires work. That requires physics energy. And so before, when we ignored the pulley wheel, all the energy was simply going into moving both the masses. That's not the case in this problem. In this problem, we also have to include the energy needed to make the pulley wheel rotate. And that's what we get. That's why the whole system is slowed down, because we're paying out some extra energy to make the pulley rotate. If it helps, and it might, think of it this way. Think of this as being an extra fee or a tax that you didn't consider before when you were counting up how much you paid in energy terms to make the system go, right? So we all know that if you go to the store and buy an item for, say, $10, what really comes out of your pocket isn't $10, right? It's 10 plus some extra money because there's tax that's assessed on that. And that's the same situation here. We have a total amount of energy which we have to distribute between both the masses and the pulley wheel. When you do that, because you're putting in energy to the pulley wheel we didn't consider earlier, the speed is slower than what it was for our calculations before. In any case, thank you everybody for your attention. I am your host, Dr. Christopher Sorolla. Technical support is supplied by Sidney Gauchow and Sophia Turner. Funding comes from the University of Mississippi and the University of Southern Mississippi. We recorded this in Hattiesburg, Mississippi. Thank you to everybody for your attention, and clear skies.